All right, welcome. Today, we are going to pull back the curtain on the secret language of the universe, and that language is chemistry. It's the code that describes literally everything that changes around us, from the toast you burned this morning to the very air you're breathing right now. And the best part is, once you learn the grammar, you can speak it too. So let's start with a little question.
I mean, seriously, what could a rusty nail, a delicious birthday cake, and taking a breath possibly have in common? They seem totally different, right? Well, in the language of chemistry, they're all telling the exact same kind of story. It's a story about transformation, where the basic ingredients of stuff just rearrange themselves to become something brand new. So how do we even know when one of these stories is happening right in front of us?
Well, it turns out there are some major clues. Think of yourself as a detective. If you see something change color, or maybe you feel it get hot or cold all of a sudden, or you see bubbles and fizzing, you are witnessing a chemical reaction in real time. These are the telltale signs that the atoms are doing their thing and making brand new substances.
Okay, so here's our game plan for today. We're going to start with those signs of change. Then we'll get into the one unbreakable rule that governs all of it. After that, we'll learn how to actually write it all down correctly. And finally, we'll start sorting these reactions into different types of stories. Ready? Let's do it.
First things first, how do we go from seeing something happen, like a piece of metal burning, and actually write that down in chemistry's language? Well, just like any language, it starts with simple words.
So we could totally write out magnesium plus oxygen reacts to form magnesium oxide. But who has time for that? Chemists needed a shortcut, a kind of slang. So we translate those words into symbols, and we get this short, sweet, skeletal chemical equation. It's way faster, and anyone, anywhere in the world can understand it.
But hang on a second, take a closer look at that equation. On the left side, we start with 2 oxygen atoms, right? The little 2 after the O, but then on the right side, there's only 1. Where did the other one go? It can't just vanish. This tells us our skeletal equation, it's not the whole story. Something's missing.
And that little mystery brings us to the single most important rule in all of chemistry. Seriously, this is the golden rule. It's the grammar that holds this entire language together.
It's called the law of conservation of mass. And it's an absolute. You can't just poof an atom into existence, and you definitely can't have one just disappear. It means that for every single element, the number of atoms you start with has to be the exact same as the number of atoms you end up with. No exceptions.
So, here's the bottom line. A chemical reaction isn't some magic trick. It's more like a cosmic square dance. The atoms you started with are all still there at the end. They've just switched partners and rearranged themselves. What goes in must come out. And our job is to make sure our equations show that perfect balanced accounting.
Okay, so to respect that law, we have to balance our equations. Now, I know that sounds kind of intimidating, but trust me, it's really just a logic puzzle. And we're going to walk through exactly how to solve it step by step.
We're going to tackle this one right here, iron reacting with water. As you can see, right now it's just a skeleton, and it's totally lopsided. We've got 1 iron on the left and 3 on the right. Yeah, that's not going to work.
We're going to use what's called the hit and trial method. The first step is super important. Imagine drawing a box around each chemical formula. That's our reminder that we cannot, under any circumstances, change what's inside the box. We can only change how many boxes we have. Then we'll just list them, balance them one by one, and do a final check.
So here's our starting head count. You can see the problem right away. We're short on iron, and we're really short on oxygen on the left side. Our whole job is to add numbers out in front of the boxes, we call those coefficients, to make the columns match. A good pro tip, start with the most complicated looking molecule, which here is that iron oxide Fe3O4. It's telling us we need 4 oxygen atoms on the right, so let's start there.
Okay, to get 4 oxygens on the left, we need to put a big 4 in front of the H2O. Boom, oxygens are now balanced, 4 and 4. But, oh wait, that move just gave us 4 times 2, that's 8 hydrogens on the left. No problem. To fix it, we just go to the other side and put a 4 in front of the H2. Now we have 8 hydrogens on both sides. Almost done. We just need to fix the iron. We have 3 on the right, so we just put a 3 in front of the Fe on the left. And let's check. 3 iron, 8 hydrogen, 4 oxygen on both sides. We did it. It's balanced. Oh, and those little letters in parentheses? They're just extra info. S for solid, G for gas.
Fantastic! See? It's just a puzzle. Now that you can read and write this language, we can zoom out a bit. You'll start to see that reactions tend to follow a few common patterns, kind of like movie genres. You've got your comedies, your dramas. Let's look at a couple of the biggest ones.
First up, we have the combination reaction. This one is basically the getting together story of chemistry. You have two or more simpler things, we'll call them A and B, and they combine to form one single, more complex thing, AB. Simple as that.
So, what does a combination reaction actually look like? Well, remember our magnesium equation from the beginning? If you were to do that in a lab, you would see this absolutely dazzling white flame. It's a total light show. That bright light is the energy being released as magnesium and oxygen combine to form that new white powder.
And on the flip side, we have the breakup story, the decomposition reaction. This is the exact opposite. You start with one complex thing, AB, and it breaks down into two or more simpler pieces, A and B.
And what's the visual clue for this one?
Well, imagine you take a plain white powder, like lead nitrate, and gently heat it. All of a sudden, you'd start to see these plumes of brown smoke coming off of it. That brown gas is your big clue, your smoking gun, really, that the original compound is breaking apart, or decomposing.
So let's just put that all together. Combination is about building up, and you'll often see energy like heat or light being released. Decomposition is about breaking down, and you'll often spot it because of a color change or a gas being formed. Now, there are definitely other reaction types, but if you can get these two down, you're building a fantastic foundation.
So there you have it. We've gone over the clues, the unbreakable law of mass, the puzzle of balancing, and the main story types. You now have the basic toolkit to start reading and writing in the language of chemistry. So here's my challenge to you. Look around. The next time you see something change, food cooking, a firework, anything, just ask yourself, I wonder what the chemical sentence for that story is.